So, welcome everybody to this last day of the research week of SURF. I think we had some very interesting last days with very interesting speakers. So this will also be an interesting session, I think, with two speakers we have for you today. Shane, Oseasnain, I hope this is the right pronunciation. It is typically Irish, and Thomas Geenen. So today in this session we will talk about digital twins and how digital twins will help, let's say, solve our solutions or our problems with Earth. This will especially be the attention in the second presentation. But in the first presentation, we will start with Shane. And Shane, I will shortly introduce Shane. He is currently working as a program director at EASY. And EASY is linked to the Technical University of Eindhoven. But before he started there, his job, I think now it's 2 years ago, he was graduated in Ireland as an electric engineering, and after his study he began his career at Philips in Eindhoven, near the so-called pilot factory in the key model group. And then he followed some next nice steps also at Ericsson as an manager for different innovation projects, but now I think he's enthusiastic working in building all kinds of communities in AI and also in digital twins. So Shane, I think it's a good moment to start your presentation about what it is, digital twins. I think in our meeting we were talking about terms like hybrid twins, swans. So I think that's interesting to know, and also to have some looks and some moonshots from your side. So please, Shane, start your presentation. Well, before you start your presentation, you can ask questions in the chat. You can start it live after the presentation of Shane. That's, I think, how we will do this session. So please, Shane, you can start.
Thank you very much, Eric. So today I work for EASY, the AI Systems Institute in the Technical University in Eindhoven. And that's my interest. So my interest is really AI, not primarily digital twins, but twins are a wonderful way, a very interesting way to find your way into AI. There's a lot of synergies between them. So whenever I give a talk about twins, or I meet someone who has questions about twins, the first question is always, what is a digital twin? And that's because there are different interpretations. So I thought it was useful just to have a look first at what that is. So if you go back to the origins of a digital twin, it's a term that's been around since the beginning of the year, to say the early noughties, so the 2000 pluses. And basically it consists of a physical thing and a virtual representation of that physical thing. And what's different maybe to just say a CAD model or anything else is that there is some sort of a data connection that brings these two into line with each other. So that's the idea of a twin. You can imagine, just like human twins or animal twins, that there's a sort of a similarity or a copy nature of a twin. And that provides all sorts of opportunities. And those opportunities then are the information that you can extract from the virtual copy. What can be made into a twin? Well, pretty much anything. And that's something I want to emphasize. It's not just about any one type of area. And in practice, what you see is that there are twins even at the small nanoscale, all the way up to the enormous national. And I think later Thomas is going to talk even on a global scale about building twins. But you can also have twins of mechanical objects, but also of biological entities, so people. And these are very, very different, of course, in their nature and scale. But the concept is being applied to a very wide range of areas and backgrounds. So different kinds of physical entities are being copied into the virtual space, and data is being used to keep them aligned. And it's not just that you can say have a twin of something mechanical or electronic, but you can and biological, but you can also bring them together. So I always find this a very nice example, the idea that you've got a heart and a pacemaker. They're very, very different. Heart is obviously very complex biological, and a pacemaker is an electromechanical device. But the fact that you can put the two of these into a virtual twin means that you can optimize and you can really learn about the behavior and the impact of one on the other. So twins are very interesting for exploring these kinds of cooperative relationships between very different kinds of entities. If you go back again to where twins first came from, I know there's a bit of an idealized picture, but basically 2 weeks ago or so, or 3 weeks ago, we had Michael Greaves in Eindhoven giving a talk. And Michael is the man who made the term popular, digital twins, back in the 2000s. And he said, really it started with the product life cycle. So it started with, you design something, you get some sort of acceptance from users or from business customers, you use it for a while, and then after a while you take it out of service again. So it started with that. But then the question is, why do we have a digital twin? And I think that's very interesting. If we have a look at another slightly different curve, we see how a twin can actually impact on this life cycle. So what a twin can do is it can allow us to do faster prototyping. So it means that in a virtual space, we can test conditions more quickly and try out different ideas. So between faster prototyping, more rigorous testing when we move to scale, so we can actually get ahead of the curve before we have to before we see real traffic or before we see lots of users, we can, in the virtual space, we can do an awful lot more preparation work. And once something is in service, having all this multi-layered and very much data supported information on anything means that we can be much more proactive, much more dynamic in how we use them. So we can have more just-in-time type approaches. We can have a lot more flexibility in the way that we set up our systems. And this is also something that's very useful for remote maintenance. So if you have a very good copy or an image of a system with lots of current information about it, you can obviously, from a distance, and we've all seen that in the corona times, how important that is, that you can actually diagnose things and try to keep things working. And I always find in a twin, this is the last area that I just, where the product life cycle, where it has an impact. Twins can also help us to extend the lifetime, and this has a very important sustainability aspect. So for example, if we have a very good model of a system, we can think about when we're decommissioning or we're coming to the end of life of systems, we can think about, can we reuse them for spare parts? Can we find new purposes for them? And eventually even, can we recycle them such that we can retain all the valuable materials, minerals, and so on, and anything that's poisonous or dangerous, that we keep it out of the atmosphere and out of the ground. So the twin is a concept that goes right from the very beginning, right to the very end of any system. It has been developed as a concept because when you have a nice concept like this, people start adding their own backgrounds and their own ideas. I won't go into this in detail, but just to say that what's happened is, based upon this very simple idea of we have a copy or a virtual representation, people have added things like AI, so they came up with cognitive twins, or they've added other scientific models and they came up with hybrid twins, or they added time as a dimension, so looking at something over its lifetime and seeing how that changes. They call those digital threads. Or you have swarms, which are basically a distributed approach of agents or something like that. Front-running simulation is a term Michael Greaves used, so basically upfront early prediction as to how a system will behave. And cyber-physical systems, which are more in the control area. And other people have created models based upon their background using this concept of twin and extended the idea. So some people are system integrators. So they say, okay, we have to think in terms of system of systems. So we have multiple twins working together. And this, I would say, is more of a software approach where we talk about instances and we talk about pulling different ideas together. So based upon this very simple, and that's one of the things that confuses people about twins. You see all these other terms, but basically all that's happened is people have added other concepts and other ideas and tried to extend it even further. So easy twins to hard twins, very simple. Okay, here's an easy twin. I've already described this. Something physical, some sort of a data connection, and it's mirrored in a mathematical model of some sort. What's changing, what's making twins harder, and this is where the research is taking place, is we're adding lots of other kinds of models and information to the twin so that we can do things in the virtual space we couldn't do in the physical space. So I'm going to give a very simple example. Maybe it's a bit silly, but I like this idea. This is what I call the golden egg sorter. So this is something typically you'll see of a kind of a twin setting. Somebody has a production line. It does something. In this case, it does something with eggs. It doesn't matter. But you have some white eggs that come in, and then what comes out are some colored eggs, and they get sorted, and eventually the golden eggs get pulled away. So it'd be very easy in a way, and this is typical, someone would make a twin of a system like this. And they would add things like cameras, IoT, sensors, and try to gather lots of data, and they will pull that into the virtual space, and then they'll be able to see how it all works. And it's kind of typical. It's nice. It works. But as you can see, there's a big grayed out box here. There's something we don't know about this process. We don't know how they go from this white to this multicolored egg environment, and what happens when they come back in, because it's a sorter and there's a sort of a process going back. And this is why we need other approaches in twins, not just capturing the data. We need to build on top. So for example, it could be that we're painting the eggs. It could be that there's a mechanical process using wrappers, you know, putting foil wrappers around it. It could be that there's some heating process going on that makes the eggs change colors. Or who knows, maybe there's an Easter bunny or something that's changing the color of the eggs by magic. This is a typical thing. There's always some sort of unknown aspects in digital twins. And I think having other approaches or building other approaches on top are really what makes twins exciting. So, and that means adding human expertise. It means, so for example, people who have experts in how the system would change the color of eggs in that case, or physics first. So maybe there's some knowledge about the weight and the density of those eggs. So that might help us to predict what's going on in that area we didn't understand. Maybe there's some data we can derive from around it that helps us to also understand what's going on in that process. And also visualization. Some people think twins are only about VR and AR, but visualization for me is a proxy for exploration. So also having people, giving them the ability to explore using these new technologies and to really dive down into the virtual world helps us to see things, because we as humans have skills that no AI system has. We're very good at noticing nuances, very subtle changes. And all of this complexity requires two things. There are two big trends. One is AI. It's very difficult to take a very complex set of sources of information and bring it together just using human abilities. We need support, we need help, and we need AI to achieve that. And to achieve it, we also need a huge amount of processing power. So that's where high performance computing is so important. So this is a kind of an approach to twins where it goes beyond just copying data, but it adds all sorts of other aspects, other sources of information to make a twin a richer, more useful environment. And this helps us to understand lots of unknowns. So as you know, in the environment, there are many unknowns. In medicine, there are many unknowns. In innovation, there's inherently many unknowns. Also in our energy management, so we're doing a project here in Eindhoven at the moment of the entire 220, 240 volt system of the Netherlands, because there are so many new solar panels and wind generations and things like that. It's become very complex. There's lots of things we don't understand, so we need twins to allow us to explore, and you could even go further into space and satellite technologies. So at EASY, where I work in Eindhoven, we're working on a couple of things we call moonshots. So what we're trying to do is, and twins are a very important part of these moonshots, we're trying to take healthcare out of hospitals. So obviously still trying to work with hospitals and help them, but we also believe, and we've seen the examples of the last 2 years, that allowing people to be treated from home is very important. And that means we have to have a lot of information about people where they are. So twins are useful for that. And we also see that supply chains are completely under pressure at the moment, with chip shortages especially, but lots of other things that we can't get. So having clear oversights and understandings and being able to predict what will happen in a supply chain is very important. And also in mobility, we see that the future of mobility is self-driving cars, but we don't so much emphasize the self-driving. We're really focused on the safety, the responsibility, the environmental impact of travel and so on. And to underline all these, there's a huge amount of data management required. So we need trustworthy data that's shared between different parties. And we also need assistance, so AI, that will help to make sense of these digital twins. So that's it. We have a digital twin lab down in Eindhoven. We kind of had a soft launch a while ago, but really we started about last December, January. I also have a community of just under 80 professors who are working with digital twins in all sorts of areas, from buildings to control of systems to biology. And it's very interesting because it brings people with different backgrounds together, this concept of a twin. So I think one of the most important things is to have a coffee machine not too far from where you have your lab with some good chats. So that's it. My message to everybody: keep an open mind about what a digital twin is. Don't get too bogged down in definitions. It's basically a concept that we are adding other ideas to, and I think that's perfect. We should embrace that. So they're a tool that helps us to explore the unknown. Yeah, and that's my little talk. Thank you.
Okay, thank you, Shane, for this nice presentation. Let's see if we have some questions yet. I can't see anything yet in the chat. Yeah, maybe then I have a question for you. Yeah, you were talking about different verticals like health, like mobility, etc. Do you see different approaches in those, let's say, sectors, these verticals, between health, between
yeah, you mean like, are there overlaps, Eric? Are there ways of them working together? Well, I think there are, and I have a lovely example. So in my car, I have a navigation system, like many people, and I have two options in it. It asks me, it says, do you want the shortest route or do you want the fastest route? So it's a very binary decision. And I actually think I would love to see in the future that there are cars that also ask, can you give me the zenest route? So can you, after a stressful day, can you help me find a nice route where there's no stress, the drivers around me are not racing, and I can take it easy. So I think just a small example, but I like that idea that we can take human well-being, for example, and combine it with technology. So, but there are many, many overlaps in many ways. I see people working with cities and they're looking at human behavior as well. And I gave the example of the human heart and the pacemaker. There are people using wearables, you know, heart rate things as a proxy for diabetes. People are looking into that. There's a lot going on, and I think that's the beauty of this thing. I saw a question there in the chat as well, related to this a little bit.
What is, well, I will read it, Sagar, if you agree. What is the answer? Sorry, what is the anticipated foreseen challenges with respect to computing requirements? And are you currently using HPC? That's what Sagar is asking.
Yes, we are using HPC. We have it in the lab at the moment, and we have not enough. We see researchers very quickly are working with enormously large models, so they need quite a lot of power to manipulate those models and to research with them. Just to go back to the first question, how much work is it generally to set up a digital twin? The reason we set up this lab in Eindhoven was actually, it was a bottom-up thing. So we had researchers who came to us and they said, we're employing a PhD student and it takes them about a year before they've worked out how these tools work and before they build their models and before they integrate their data, and it's too slow. We'd like them to do research on their core activity, not on setting up the environment. So it does take a lot of effort if you don't know what you're doing, but that's the reason we've set up this support infrastructure to help researchers. Yeah, and reuse what the output is at the end of the day too. So when a PhD or someone leaves, you often have the problem that when they finished, that everyone's looking at each other saying, I don't know what they did. I don't know how it all worked. It was all magic. It was the Easter Bunny again. But so that's part of it.
Yeah, so we have maybe some last room, 1 minute for Ed's a question, Ed Kuipers, about standards. Are they being developed and recommended?
Yes, they are. There is one, it just escapes my mind, but there are standards being developed and it's a big issue in Europe. However, it's not a simple discussion because obviously you have the complexity of different kinds of systems and technologies, but also there's a question of trust. So if you have a supply chain, for example, and you want to share models from suppliers to customers to their customers, there are many people, for good reasons, who are saying, am I taking risks with my IP? Am I maybe doing something a bit silly if I put it up there on the internet and people can look at my CAD drawings or something like that. So, or the behavior of my system. So there is a lot to be worked out yet in terms of security and privacy and these aspects. And that I think will be it's a bottleneck to standards at the moment. But at some point we will need common approaches. I personally think, by the way, other approaches like knowledge graphs and other frameworks, maybe it doesn't need a standard, will be a big help.
Yeah. Okay, thank you. Well, I suggest to go to our next speaker because of time. I see there's another question, but let's see if we have time at the end responding to these questions. Otherwise, of course, you can send an email directly to Shane. Well, let's introduce Thomas, more or less. We now going to, let's say, the second presentation about, well, Destination Earth. I think digital twinning was a term more or less started in industry, but, well, is now, let's say, broadly supported by other, well, research areas. Very fascinating, Destination Earth. Me and Thomas had a short introduction this week. He is living in Florence, and working in Bologna. Well, to start, he graduated in Geophysica. His master's, he did some PhDs in Utrecht as well. He worked as a colleague in the past for SURF as an HP solution expert, and then he started a job at ASML. He did, well, of course, he was there, I think, also an HPC expert in supporting all kinds of processes. And now, shortly, or I think early this year or last year, you started at ECMWF, and yeah, I'm very curious about your presentation, Thomas. So please, the floor is yours.
Thank you, Eric. Yes, indeed. So I will talk about the digital twin of the Earth. And thanks, Shane, for the nice introduction. So my next slide, I can be very quick. So indeed, digital twins, you can make a digital twin of basically anything, even when there's no physical counterpart. But in our case, there is absolutely a physical counterpart. And yes, it's in production. So we really focus on the production part of the life cycle of a physical asset, in this case, the Earth. In our case, we're looking at climate change and extreme weathers and how that interacts with human activity. So we're running simulations of the Earth, and we also have a lot of observational data from satellites of the Earth. We are able to monitor the performance and predict the performance of our numerical models, also based on the observations that we're doing. And we want to provide, as part of the digital twin, a means for technical interaction with the simulations in a way that has not been done before. And that will allow for scientific theory testing and also for scenario testing to understand what kind of climate change mitigation strategies will make sense and what the impact of that will be. So when you look at what ECMWF is doing, so we're the European Center for Medium Range Weather Forecast. So we're doing numerical weather forecast, and we're doing that on a global scale. And typically we give those background global models to national weather institutes, like for instance, KNMI, to build the regional models. So we have a lot of experience in capturing data from satellites, from planes, from buoys, from ships, from ground stations to collect a lot of data. And we also have a lot of experience in system Earth modeling. So we run high resolution coupled models where atmosphere, oceans, ice, land effects, you name it, is incorporated. And on top of that, we are continuously incorporating observations in a mechanism that we call data assimilation. So that means that we have sort of the basic building blocks for a digital twin are already there. So there was a question in the chat on how much work is it? Well, to build a system like this, you can imagine that will take decades. But we are in a good situation that has already been done. So we only, which is still quite a lot of work, have to build sort of the digital. You have to change that into a digital twin. So when you look at this picture here on the bottom, you see that we have all these observations on the left-hand side. We then have the data assimilation and the simulations running on a high-performance computing cluster. And then we generate products, which are information products, and we feed that into a system that allows you to reason about your physical asset, in this case, the Earth. Now, as an example of that, we here have a heat wave in Russia, where you see that based on predictions about climate change, you can say something about the regional effects. Then you can say something about the impact on that on socio-economic aspects like crop failures. There can be forest fire, which causes air pollution, which has an impact on health and mortality. Crop failure will have an impact on wheat prices. So you will have all kind of social economical impacts that we incorporate in these digital twins also. And it allows us to reason about the impact of the Earth and the impact of climate change and the impact of extreme weather on socio-economical aspects. Now, why do we want to do this? So the cost benefits, typically for digital twin, you always have to do a cost benefit assessment. So in this case, it's pretty easy. For instance, the financial impact of climate change will dwarf the costs associated with COVID, for instance, and also the number of the human loss is as a result of climate change is estimated to be quite high, and also the human loss as a result of extreme weather is definitely very significant. So the reason to build such a digital twin is quite obvious, but you have to change the current way that we provide the information of numerical weather predictions and climate change to decision makers in a way that they can actually act on that information. So here's a quote from Christian Kirchsteiger, who is basically saying, like, this is all very nice that you're doing all this simulation, but most of the simulations are quite black box. And it's really difficult for people who have to make decisions to base that on the output of simulations. So you have to translate the outcome of simulation into something tangible and something that you can act upon. On top of that, we have a huge data problem. So these digital twins currently, how we envision them, will produce a petabyte of data every day. So to process that and to make sense of that takes an insane amount of effort. So for instance, we run very high resolution models for a couple of days, and it took us 6 months to actually process that data and make sense of it. So there's a huge challenge there to do something. But we do need to have these high resolution global models because we need to capture certain basic physics. So we don't have to capture anything, right? Numerical simulation is always an estimation, right? You never resolve all the scales, but some scales are really important. And unfortunately, some of the scales that are really important are on kilometer scale resolution. And that means we have to run these numerical models, which will generate the amount of data that I just mentioned. And is that a problem? So yes, it's a problem. Currently, we're using the pre-exascale systems that are currently being built in Europe. We can run at kilometer scale, but we want to take it a little bit further. And if you just extrapolate that and you want to solve it like a brute force, you will need like roughly 100 billion times compute power that's currently available. So we have to do something smarter. So what can we do? Can we cut some corners? Well, it's not so easy because the physics is really complicated. These systems are highly nonlinear and highly chaotic. So being able to predict the state of the Earth a couple of 100 years from now, you have to basically solve physics laws. There has been an attempt to using machine learning to predict the state of the Earth in a few 100 years from now. That is not being very successful so far. There has been some successes, but more on the short term, more in the linear regime of the Earth, and also more in the interpolation part. And it's really difficult for these models to extrapolate to states that have never seen before. Also, by incorporating more and more physics in these machine learning models, they also become more and more computationally intensive. However, we do see a very interesting use of machine learning and AI where we run our physics-based simulation forward in time, but we snapshot that every so often. And from those snapshots, you can do, using machine learning, high fidelity simulations close to those snap points, which allows you to do scenario evaluation and what if scenario evaluation around those snap points. And that's already very useful. Now, to summarize, on the right-hand side, you see the socio-economical impact sectors that we mentioned before, like health and energy. We feed those models into our digital twin of the Earth. On the top part, you see the capabilities in terms of data assimilation, Earth observations, Earth system models, and on the lower part, you see the digital technology that is needed to actually run the digital twins. And that incorporates indeed big data, HPC, smart sensors, more the hardware part of it. Now, another interesting aspect of the digital twins, you have to bring the output of your simulations to the scale and the level that actually people feel the impact. So this is an interesting example where they took a global simulation, a digital twin of the Earth, global, and extrapolated apart onto a regional model where they looked at meter scale simulation of climate change impact on a city. In this case, in Paris, they looked at the Paris Olympic Games 2024 and how climate change would potentially impact, for instance, urban movement. So how people move inside a city. And then you can start to think about ways to improve cities to deal with that. So that is a real tangible outcome of such a digital twin, where you can actually reason on a specific topic and a specific region on how climate change will impact certain events. So that was the part on digital twins. Eric, I'm looking at you. I can have a few slides on.
Yeah, that's correct. You have some let's say at least 5 to 7 minutes to speak, so it's okay.
Good.
Yeah.
So Destination Earth is a European project. Is being executed by 3 entities: ESA, EUMETSAT, and ECMWF. So we are responsible for the numerical models and building what we call the digital twin engine. Basically, is the plumbing that allows you to run digital twins. ESA is responsible for the core platform. It's basically the user-facing part of it, where you will interact with these models, and EUMETSAT is responsible for the data lake. We will execute it in 2 phases. So we have a first phase. We will basically do a pre-production implementation of Destination Earth, where we basically show the capabilities. And then in further phases, we're actually going to put this in production. So it's very important to realize this is not a research project. This is an operational project. So we're actually going to put this thing in production and we're going to maintain it. Like we also have our numerical weather models in production for a couple of decades now, and we run it on production every day. So we produce numerical weather forecast 3 times a day, and we're going to do the same with the digital twin. So it's not going to be something that is going to go away after we figured out how to do it. We're going to just dissolve it again. So when you look at a structure, you have in your user groups that are going to interact with your digital twins. You have the digital twins themselves, and in the background, you have more like the technology implementation, high performance computing, your data sources that includes observational data that is flowing from your sensors in the field. That can also you can also bring your own data sets to that data platform to use that for your digital twin evaluation if you have a new data set or an interesting idea on how to use specific data that has not been made available so far in that platform. As I mentioned before, we're going to focus on 2 types of digital twins. So one is on climate adaptation, and the other one is on extreme weather. I guess we all remember the severe rains we had last year in the south of the Netherlands. So these kind of effects we also want to capture in this digital twin and allow policymakers to understand the impact of certain decisions they're making and be able to simulate that in real time. Now, funding opportunities. So Destination Earth, we're doing a lot of tendering. So for instance, the complete digital twin for climate prediction, climate mitigation, and extreme weather digital twin, we are currently in the tendering process to outsource that to consortia in Europe. And then we're also going to have tenders on specific use cases. So if you have an idea on how to use the digital twins for a specific use case, then there will be tenders in the coming years and also in the following phases, where we will invite you to work with us on developing additional digital twins for specific cases and scenarios. All right, and that was my presentation. I'd like to thank you.
Okay, well, thank you, Thomas, for this very nice and interesting presentation. Yeah, I see some questions already in the chat, but maybe I have a first one because you were talking about, let's say, well, predicting heavy showers in the south of the Netherlands, for example. We had it last year. Are you able to, well, predict for this summer interesting things already?
So I think we're good so far. I have not seen any predictions so far, but maybe it's interesting to realize that the heavy showers of last year were more or less predicted pretty well.
Okay.
Not that for numerical weather people, they did not come as a surprise. But of course, the impact of these heavy rains on cities and communities, that's a different story. So that's why also we want to have the digital twins to make that translation to something that we predict. So in a numerical weather, so in the weather community, it was known that something really bad was going to happen. But outside of the community, it was less known. And what to do with that information and how to act on that one and be able to run scenarios on what if I do this, then what will happen. That is something that we want to bring to the table with this Destination Earth.
Yeah. So it's a little bit also the communication, let's say, which need to be started. I mean, that's okay. Thank you. Let's see. Well, I see Annette has a question. I will read it. Then Thomas, you know, SURF. Yeah, that's correct. How could SURF help the Dutch community to participate in the Destination Earth activities? So it's for us indeed a very important community. How can we contribute as SURF?
Well, we're currently running tenders, so I cannot say a lot about, but there's definitely from the Dutch science community and also from the Earth observation community, we've seen responses. So I expect that they will actively participate in Destination Earth in the coming years. So yeah, we will work with them for sure.
Okay. Yeah. Okay. Thank you. And how can research be part of this as well, or what is the role of researchers in this kind of, let's say, consortia or developing those twins? Can you tell something about that?
Yeah. So what we typically see is as a response to the tenders that we are publishing, we see that these consortia are quite big. So a lot of universities and a lot of research institutions, they collaboratively respond to such an invitation to tender. So the research community is very much involved. Also the Dutch research community, both on extreme weather, but also on climate adaptation.
Okay, thank you. Well, I see Shane, you raise your hand.
Yeah, I did, and Thomas, thanks. That was brilliant. I really enjoyed learning about this project and this research. I think I'm triggered a little bit by Eric's question to me earlier, and I'm thinking about how can we take this information and put it into the hands of ordinary people, you know, to make the consequences of their actions more transparent, because obviously global warming is a sort of a longitudinal, long-term process.
Right.
Well, maybe not so long-term anymore, short-term, but it's not at the level of it'll be raining on Tuesday if you drive your car today instead of cycling or something like that.
Indeed. So it's exactly that translation. So ideas that are floating around is how can you stream data from these digital twins or specific information from these digital twins to applications that can then translate that information into a specific case and then translate it into actual tangible information that you can act on. So digital twin is definitely not like a barrage or a tsunami of data that you just dump on somebody's plate and say, well, here it is. You need applications that digest that information and present it in a way that you can actually act on it. So that is one of the big challenges for digital twins, and we are working on solutions in that field.
Very interesting. Thanks.
Welcome.
Okay. Well, I think I don't see any questions anymore. There was a question. Oh, there is now a question of Kees Hof. Shane already mentioned this aspect. You need trustworthy with the data do you face any issues about the source of your data for this for the EU work?
So that is an interesting question. So of course, for weather prediction, we have the same. So we over the last couple of decades, ECMWF and others have invested a lot of time, a lot of energy in making sure that your predictions are trustworthy, the data is trustworthy. So we have a lot of experience that we bring to the table. And for climate models, we will use the same kind of technology. So for instance, we're doing ensemble simulations. For climate, we will do the same. So you will get a statistical understanding of the quality of your models. And also we will do, we have a lot of observational data as well. So we can also feed it back. So we can run our simulation, actually understand how in reality that materialized, and understand what it means for the quality. So we have a track record in that, which I think is pretty good.
Okay.
Can I add one thing? Is that okay? Just a quick comment. Twins need data. They're better when they have lots of data, and luckily we're in an era when there's lots of IoT and lots of information floating around. But sometimes there's also information that's hard to find. So I'll give an example. Again, it doesn't have to be, but okay, I'll give you actually a human one, because I could have given a motorized one too. But it's unusual for example, to have data on what's happening when people are having a hypo, when they have diabetes. So they're having a sort of an attack. We can have lots of data on their normal lives using these sensors. We can see what their sugar levels are. We can measure their heart rates and yada, yada, yada. But we don't have a lot of data on, when it really goes wrong. Those are events. They're very seldom, hopefully. So we can use twins as well to synthesize and merge data for these seldom events, but combine them as well with the easier to obtain, so the everyday non-attack situations. And that gives us better data sets, and those better data sets are really useful for AI. So twins are kind of a flexible concept, but they can make data more trustworthy, and they're an important part of that discussion.
So yeah, it's interesting. For us, it's the same. So the good thing about extreme weather events is that they're extreme, so by definition, they don't happen often. So also for AI and machine learning, that makes it really hard to train on something that shouldn't occur. But yeah, there's ways to indeed to use your existing data to still be able to predict extremes as well. But, yeah.
Okay, thank you. Well, I see a question of Sagar in the chat. Are you looking at federated computing, or are you planning to? Yeah, maybe you can explain a little bit.
Yeah. So for
federated computing means for you.
Right. So for Destination Earth 1, pre-exascale machine is not big enough. So we're going to use all of them as soon as they get in production. So Lumi will be the first one in Finland. Then we have Leonardo in Italy, and then we will have Mare Nostrum 5 in Spain. We will run on all of them. We will not run simulations across HPC systems. I think that is probably not a very brilliant idea, but we will definitely run different components of digital twins across these different systems, and also make sure that there is a federated data model. Of course, you want to keep the data where it is, right? You want to run a simulation where your data is. You don't want to move these hundreds of petabytes of data across Europe, but you will have visibility on the data and understand where the data is and so on.
Yeah, okay, thank you. Well, I think, we have 1 minute left. I'm looking into the chat. Cases, thanks to you. His questions were based on the data repository of DANS. Well, you are familiar with that, I think. Okay, well, I think then some last words, because I want to thank you, Shane, for your wonderful presentation, and hopefully we will meet very soon at EASY and building and supporting your communities. And Thomas, I want to thank you as well. Good luck there in Italy, in this wonderful city, Florence, with your family and your kids over there. So Thank you, and yeah, I want to thank the audience. If you have some questions still, please let us know. Send us an email to Surf, and we will send that to Shane or Thomas, or you can send it directly to them. It's okay. Okay, thank you again, and see you next time.
Thanks.
Bye bye.
Thanks very much, Eric. Too. Okay, take care. Bye bye.